Alright, so now we're going to be looking at polynomial functions, linear factors, and zeros, and we're going to be graphing cubic functions. So let's recap a little bit and talk about what the zeros of a function are. So as you can recall, whenever we studied quadratic functions, we looked at parabolas, and we said that the zeros of a function are the values of x that the function achieves whenever y equals 0. So we're looking for the value of x when y is 0. So those are the zeros of the function. Now how can we find them? Well, we found them in many different ways. We factored, we used the quadratic formula, we graphed, we completed the square, we used the square root method. So there's many different ways that we found the zeros of a function. So here's a summary of all the methods that we used to find the solutions of a quadratic equation. We completed the square, we factored when possible, we graphed, we took a square root when b was equal to 0, or you could always use the quadratic formula. So we're going to be using these different methods to help us solve higher degree polynomials. So we're going to be looking at higher degree polynomials and trying to find the zeros of these polynomials using some previous knowledge that we already have about solving quadratic functions. So remember, whenever we solved quadratics, the very first thing we always wanted to look for was a GCF. Well, here in this cubic function, I can see that I have a GCF of x. Each term here has an x in it. So I'm going to go ahead and factor out an x from each term. I'm only allowed to do this because every single term has an x in it. Now, you can see we have just a lonely x out here, and then we have it multiplied times this quadratic function. Now, we have many methods to solving quadratic functions. We have factoring, completing the square, using the quadratic formula. So we always want to check to see if something's factorable, because that's going to be the easiest method. So the factors of x squared are x and x. Factors of 15 are 3 and 5. Different, biggest product is negative. Go ahead and check your inners and outers. 3x, negative 5x, that gives me negative 2x, so I know I did it right. So now what you can see is you have something times something times something equals y. Now remember, to find the zeros, I'm looking for the values of x that make y equal to 0. So I'm going to set y equal to 0. And I want the values of x that are making y equal 0. So now this is exactly how we solved the quadratics before, except for now we have this extra term. So we're going to set each term equal to 0. So I have x equal to 0. I have x plus 3 equal to 0. And then I have x minus 5 equal to 0. So it's very easy to see that my zeros are going to be 0, negative 3, and positive 5. And yes, we like to write our smallest term first. So solving those three mini equations, these are the solutions or the zeros that we find for this cubic function. So at these three values of x, my function will cross the x-axis and have a value of y equals 0. Now, of course, you can take these values, plug them back into the original equation, and you should get y equals 0 for all of them. Whenever we learn about quadratic functions, we looked at how zeros, roots, solutions, x-intercepts, all of these things really mean the same thing. They mean the x values that make my function y equal to 0. Now, these are also equivalent statements. So x minus b is going to be a linear factor of the polynomial p of x, where b here is your solution or your root, okay? So b is the 0 of the polynomial function y equals p of x, okay? So whenever we're looking at the graph, we call it the 0. b is the root of the polynomial equation. So remember the difference between function and equation. Function's y equals, equation is equal to 0. And b is also the x-intercept of the graph, y equals p of x. So we should kind of recall some of this vocabulary. The only thing that might be a little new is looking at x minus b being a linear factor. So what if we want to graph these higher degree polynomials? How do we do that? Well, remember, you can always refer back to making a table when you graph. That is always your plan B. That is always what you want to do if you have no idea what to do. So remember, to make a table, you just do a little t-chart, right? You pick the x values, you plug in those x values, and you find the corresponding y values for our function. Now, the key to making a table is to have some idea of what x values to choose. Now, what we're going to be doing is we're going to be using the information that we already know about the graph, like the zeros of the function, and then once we know the zeros, we're going to be picking x values that are near our zeros to kind of help us figure out what the behavior of the graph is. Now, these graphs are going to be sketches, purely sketches. They're not going to be exact, they're not going to be precise. It's too hard to get precise and precision whenever you are graphing these by hand, but they will be pretty close and accurate as long as we use the zeros and then plug in and find a table of values. So here is a step-by-step of how to graph a higher degree polynomial. So this is going to be very useful. So the first thing is you want to make sure you're in standard form. If your function is factorable, you want to go ahead and try to factor it. And once you have factored it, you want to set each of the factors equal to 0, and you want to solve for the x value. So this is very similar to solving a quadratic, except for you might have 3 or more terms that you're setting equal to 0. Now you want to plot those zeros on your graph, so those are going to lie on the x-axis, and then we're going to make a table of values to fill in all that missing information in my graph. So we're going to pick numbers between the zeros. Now, if our function in standard form is not factorable, we're just going to go straight to making a table of values, all right? So you just pick x's and you solve for y. Alright, so now we're going to sketch the graph of y equals x cubed minus 4x. Now remember, this is just going to be a sketch because we can't have a precise graph by hand. The first thing we want to do is factor if it's factorable, and this one is, it has a GCF of x. So we're going to go ahead and pull the x out. When you factor out the x, you could see that the quadratic term factors again into x minus 2x plus 2. Now, since we're trying to find the zeros, we're going to set each of these terms equal to 0. Doing that, we're going to find that x equals 0, x equals 2, or x equals negative 2. So we're going to go ahead and plot these points on our graph. These are our zeros. Now, the next thing we're going to want to do is pick points between these values. Now, we can also use our knowledge about end behavior. We know that since this is a cubic function, that the ends of the graph go in opposite direction. And since the leading coefficient is positive, it's going to start down here and go up over here. So I should kind of know what this graph is going to look like before I begin. Now, picking values, let's go ahead and just pick a value to the left just to make sure that we're right. So I'm going to pick negative 3. Now, in between, I'm going to pick negative 1. In between the other 2 points, I'm going to pick positive 1. Okay, so I picked one from over here, one from here, one from here. And let's go ahead and pick a point over here, so let's pick positive 3. So now we're going to go ahead and plug those into the function and find our y coordinates. So as you can see, since negative 15 and positive 15 are off my graph, we still know that since it's cubic, we're going to start down here because our leading coefficient is positive. We're going to go up, we're going to come down, hit our points, and then we're going to end up going back up. So that's exactly what we're going to do. We're going to start down here, we're going to go up, we're going to hit this point, which is in my table. We're going to come back down, hit this point, and then we're going to end up going back up. Okay, so again, remember, this is just a sketch, but since it's cubic, I know that I better have, I can have 2 turning points, and I know that the ends will go in opposite directions. Since the leading coefficient is positive, I know that I'm going to start down low and end up on the right going up. So here's the graph actually graphed inside of GeoGebra, so it's a little bit more accurate, but you can see it looks very similar to the one that we just did. So we have our zeros that we found by factoring and solving. We have our negative 1, 3 and positive 1, negative 3 that are points that we plugged into our table, and you can see that it looks very similar to the graph that we just sketched. Now we're going to sketch the graph of y equals x cubed. So y equals x cubed is actually the parent function graph for all cubic functions. So just like whenever we studied linear functions, y equals x was the parent function for linear. y equals x squared was the parent function for quadratics. Well, when we're talking about cubics, this is the parent function for cubic functions. Now, this function is obviously not factorable, so we're just going to go ahead and pick values to plug into our table, and we're going to plug these in for x and solve for y. Now, because it's a cubic function, it's an odd degree, right? So I know that it's going to go down and then up because our leading coefficient is positive. Now, going ahead and graphing the points that I just found in my table, I get -2, -8. I get -1, -1. 0, 0 is actually my only zero of this function. +1, 1. And then I get +2, 8. So connecting these, try to make a smooth curve, right? Because it's a function, smooth curve as best as possible. So connecting these, I know I'm going to start low. I'm going to come up here, hit these points, and then I want to come up here and connect with that dot. So as smooth as possible. And this is going to be the parent function y equals x cubed. So now we're going to sketch the graph of y equals -x cubed minus x squared plus 6x. Now, because it's a cubic, I know that the ends of the graph will go in opposite directions. Because it's a negative leading coefficient, I know we're going to start up and then we're going to end up going down in opposite directions. Now, yes, this guy is factorable, so let's go ahead and factor out. It looks like we could take out a -x. We want to take out a -x so that whenever I factor this, my quadratic that will be left over will be positive leading coefficient. So -x, I'm going to be left with x squared plus x minus 6. So be careful there with your signs. Now factoring this quadratic. Remember, if the quadratic is not factorable, you can use other methods to solve. Different signs, biggest positive here. So setting each of our terms equal to 0, we'll see that our zeros are going to be x equals 0, x equals -3, and x equals +2. So graphing those zeros. So now that we have our zeros plotted, we want to pick values that are in between our zeros. Now we also are going to pick values to the left and to the right just to make sure that we know exactly the shape of our graph. So I'm going to pick -4. In between -3 and 0, let's go ahead and pick -2 and -1. You don't have to pick both, but I like to be precise. Let's go ahead and pick in between here, 1, and then let's pick a point to the right, so let's pick +3. So we're going to go ahead and plug these into our function and see what we get. So now that we have our additional points, yes, the point -4, 24 is off our graph, but at least that we know -4, 24 should be up here somewhere, which is exactly what we thought. We should be starting up on the left, and then 3, -30 is down here. So we should be starting up and going down. So going ahead and plotting the points that we found in our table, -2, -8, we have -1, -6. And I do think it's better, the more points the better. You know, you want to make this more accurate. We have 1, 4. Okay, so we know that we're going to start up top. Okay, we're going to come down and we're going to intersect at our axis. We're going to hit this point down here. We're going to go through this point. We're going to hit this 0, cross over the x-axis, hit this point, and come back down. And then we know we're going to end up going downward. Now, don't get too crazy with the ends of the graph. Even this one, I would actually prefer to maybe just go straighter down. We don't know exactly how it curves, so we don't want to make anything up, okay? So this is going to be a pretty good sketch of this function. So here is this function plugged into GeoGebra, so we can check to make sure that our graph does look pretty similar, right? So here are our zeros, and then whenever we had -2, we were down here at -8. When we had +1, we were up here at 4. So you can see that we got pretty much the same thing as we would if we plugged into GeoGebra. So we did a pretty good job doing it by hand. So now I want you to give these examples a try. Remember, zeros and x-intercepts, they all mean the same thing. X values that make y equal to 0, so you might want to factor for those. And end behavior depends on the degree and the leading coefficient. And graphing a function that looks like this, you might just want to make a table of values.